Hello everyone and welcome back. So this time we're going to be talking about the reduction of a simple distributed loading. So let's get to it. First off, applications. Why do you care about this? Well, something you probably realize is that if you have this bunk of 2x4 boards, um, you know, there's a lot of force pressing down on this beam. And now, a lot of times when we deal with these things beforehand, we would say, well, the center of gravity of this box is right here in the middle, and we then put the force down. And that works, but the center of gravity was always given. But what if you didn't have that? What if you just had some sort of arbitrary loading? How do you deal with it? How do you tell what kind of force is being dealt to this beam? How do you know what the moment is right here? So how would you reduce it to that single force and moment? Right here, we have wind pressure pressing on this triangular sail, and you're like, whoa, yes, we've gone three-dimensional with this. So how do you work with this? How do you figure out what the force is, and where does that force actually land inside of this triangular sail? Spoiler alert, integrals. Yeah, they're here. We don't have too many in this class, but you're going to see quite a few for this. So you have to think about what the equivalent force is going to be and also where it's going to be placed. So we got to think about that. So all these things we've been seeing right here where you have a bunch of arrows with a line connecting them is something called a distributed loading, because in many cases the force isn't really at a single point, it's at a long series of points. It's just spread out over the entire thing. If you're carrying a big box, you feel the weight of that box all the way across your arm that's holding the box. You don't just feel it at one magical point at the center of gravity of the box. So these can be caused by fluids, they can be caused by the wind, they can just be caused because things have size. Most things in life are a pressure, they're not a force, so they're distributed. So when we deal with this, we have to use some kind of terminology here. First off, integrals. You're going to see a lot of these little lowercase d saying an infinitely small element. And what we do is we're going to make a bunch of rectangles, and we're going to sum up those rectangles. So each of those rectangles has a little area dA. And since we have a loading, we can figure out what the force is on that point, on that area. And then eventually take an integral to figure out the total force, and then from that figure out where we can put it to have the same external effect. Many of the cases, our loading is going to be a function of x or units of force per length. This is not always the case, though. It could be something different. So if we're going to find the magnitude of the resultant force, it's actually pretty simple. You can see here that if we have a certain length and we're multiplying force per unit length, then this would have units of force. So this is our infinitesimal element of force. If we then integrate for the entire length, we will get the entire force. So it's going to be an integral here of our loading with respect to the length or the area, depending on what you have. And this will be the area under this curve. What that means is that you can numerically approximate this. In many cases, that might be the easiest way to do it, but not always. So remember that. Think about that. That can help you. And then when we have this done, we will have the resultant force, which is more or less the sum effect of this loading. But where does it go? Because you see there's this x bar right here, which says, well, that's where the force is going to be applied. Like that has the same external effect, which hopefully, like the whole, resolving all our moments and forces into a single force moment system kind of makes sense when we hit that first. Okay, but the location of the resultant force isn't terrible to get. The big thing is that it's going to be more integrals, which I'm sorry for, but sometimes these integrals aren't bad. Sometimes you don't have to have an integral at all if it's a nice shape. So to get that, what we do is we first sum for the moments. Okay, we got to figure out the moment around this. What is our resultant moment due to this distributed load? And so that's going to be equal to a distance times the force. We've already said that that force right here, this little force element, is going to be equal to the loading times the change in position. So if we integrate this, we will get our resultant moment. If you remember, when we have a resultant moment and a resultant force, we can figure out the distance to where that force could be applied to have the same external effect. This is actually just solving for the centroid, okay? The resultant moment is going to be equal to our centroid, how far we have to go to get to our centroid, times our resultant force. So if we applied a resultant force at that point, it would have the same effect as this entire loading. And you get this nice little equation here where you see we have x dA on the top and dA on the bottom, which is going to be simply the area of that element. And that dA is just taking this as the height of the element is going to be our loading, and the width of the element is going to be the infinitesimal length change. So this is an area, and that's how you can approximate this. If you can just pick a value right here and you pick a small enough value for dx, you can get a very good numerical solution. I've had students do that in the past just for fun in Excel. And I think numerics is pretty awesome. So finally, in the end, when you solve this right here, and be careful that dA does not cancel just because it's on both sides, then you will find the centroid. That's the distance from the origin to our point where this force would be applied. Okay, so we're going to stop here because we think we've done enough. We're going to do some examples of this. So we're going to do a few examples to really kind of drive this home. Make sure I'm right. Yes, the next one is going to be an example. So I hope this helps you, and I will see you all next time as we do some examples of calculating the centroid, calculating the resultant force and moment of some distributed load. Have a good day. Bye-bye.